second session is Vincent Vivier, who come from University Pierre and Marie Curie in Paris. He will talk about the use of local electrochemical techniques for the analysis of intermediates in several reaction.
Thank you. So first, I would like to thank the symposium organizer and the organizing committee for giving me the opportunity to present the work we are performing at LISE. So in our lab, we use a lot of impedance spectroscopy, and I will try to show you that we can use this technique in order to characterize adsorbed intermediates at an electrode surface. So what we want to do is to characterize the adsorbed intermediates. So this was already done in the past using the scanning electrochemical microscopy. For instance, you can refer to the work of Joaquim Rodriguez-Lopez when it was in the BART group. And the idea was to generate an adsorbate at a microelectrode and to perform the dosing of this adsorbate using a second microelectrode placed in the close vicinity. So this was the surface interrogation mode. What we want to do here is to characterize the relaxation of these adsorbed intermediates during the electrochemical reaction. So we want to combine impedance spectroscopy and scanning electrochemical microscope in order to evidence, for instance, to study, for instance, the reduction of a solid species, like in this case. I will show you an example of the reduction of copper 2+ ions in a chloride-containing solution, or for the dissolution of a metals, like the dissolution of iron. In both cases, we have mechanisms that involve adsorbed intermediates. So the outline of my talk is first I would detail a little bit the setup and the measurement principle, and then I will start from a simple redox mediator just to characterize mass transport between the two microelectrodes, and I will investigate copper 2+ reduction, hydrogen adsorption on platinum, and the iron dissolution. And I will finish by a local measurement without redox mediators. So to perform this kind of experiment, we use a scanning electrochemical microscope. This setup, I think that everybody knows now what is this kind of setup. We have a substrate, we bring a tip, a microelectrode in the close vicinity of the substrate, and we can measure the current at the tip, and any variation in the tip current will give information about the kinetics at the substrate. So now, if we do the same thing, but using transient mode, like impedance spectroscopy, we can apply a small sine wave perturbation at the substrate. So here we apply a sine wave perturbation, and we will measure the current at the substrate here. So doing this, we can generate the usual electrochemical impedance. If simultaneously we generate here a redox mediator, and we detect this redox mediator at the tip. So we also have a sine wave response at the tip. And then we can define a complex collection efficiency, N, as the ratio of the tip current to the tip of the substrate. So this is very similar to what was done many years ago by Albery and co-worker for rotating ring disc electrode. So how it works? What we will do with this system, we will perform electrochemistry at the substrate, and we will detect an electroactive species at the tip. So at the substrate, we can consider we have this simple reaction mechanism, so with an adsorbate intermediate here, and at the tip, we dose the red in solution. From an experimental point of view, we measure this collection efficiency, the ratio of the tip current to the ratio of the tip current to the substrate current. But we can split this contribution into 3 different contributions only by introducing the flux at the substrate. So I introduce the flux here and here for the substrate, and at the tip. So this term here and this term. And now I can combine this term and the first term here, which is the flux at the tip to the flux at the substrate is determined completely by mass transport of electroactive species from the substrate to the tip. The second one is the kinetic efficiency of the tip process. So if we choose a fast system for the tip reaction, this term is constant. And then this one is the kinetic emission efficiency of the substrate, and it contains all the information on the kinetic at the substrate. And this is the term in which we are interested in. So what will we get? So we measure, this term. We can determine this term and this term. So the interesting part is N sub. N sub here can be can be obtained here from this equation. And this equation arises from the fact that at the substrate surface, we can split the current in two contributions, the flux and the current that reacts due to the formation of adsorbed species, so 2D formation, or of the film at the electrode, 3D formation. So here, what we get at the end, it's the equation of a semicircle. And this semicircle, if we plot this equation, we obtain this Nyquist representation. This contribution corresponds to the relaxation of adsorbed intermediate. This one corresponds to what's happened at the substrate, but only with the component of the flux of the current. And this term, when the frequency turns towards the infinity, contains the information about the kinetics of processes occurring at the substrate. So just two last equations. We are measuring the complex collection efficiency, and simultaneously we can measure the impedance at the substrate. So if I introduce in the previous equation the potential here, I can here identify this term as the impedance, and the previous equation here give this relationship, and this term is a capacitive term that allows to evaluate the frequency dependence of the amount of charge stored at the interface, and the integration of the low frequency limits determined by this equation allow to evaluate the charge stored at the electrode surface between these two potentials. So what can we measure with this kind of technique? So first, I will consider a simple redox mediator, the ferricyanide redox couple, redox mediator. I can reduce this species at the substrate and oxidize it back at the tip. So if I perform a usual impedance spectroscopy at the substrate, I get this plot. So we have the charge transfer resistance in parallel with the double layer capacitance. And here what we get is the diffusion at a microelectrode, so a flattened semicircle here. Now if I have a look on the complex collection efficiency, I just have the transport of this species between the substrate and the tip. And what I get here is the signature of the mass transport of this species between these two electrodes. I can now calculate N sub, and because I have no adsorption at the electrode, I get a single point centered at the 1 value. And it's only a real value. So with this first experiment, I can completely characterize the diffusion between the substrate and the tip. If I now consider a much more complicated mechanism, that is the reduction of copper 2+ in chloride-containing solution. So this is the CV curve of the copper 2+ in this solution. And I perform also an impedance measurement. So I have a flattened semicircle here and the diffusion at a small electrode. If we have a look here on the phase angle in order to see what's happened in this domain, here we have indeed two time constants. The first one corresponds to the charge transfer resistance, and here this one may be ascribed to the relaxation of adsorbed species at the interface. And this last time constant is the diffusion of redox species. So this can be, I lost this, if I perform the complex collection efficiency experiment, I obtain something similar than the previous experiment. If you go back here, something that contains the diffusion. But if I now calculate n sub, I obtain a summer circle indicating that I have an adsorbed intermediate at the interface, and the relaxation 20 Hz is in good agreement with the relaxation here, evidence on this body plot. So if we are with this result, we can try to investigate something much more complicated. So we can go to the hydrogen adsorption on platinum. So we are interested in this domain. So we scan the potential on this area. And for hydrogen adsorption on platinum, we can usually invoke two different mechanisms. The first one is the Volmer-Revsky, and the other one is the Volmer-Tafel. So what we did the same experiment than before. So we calculate first the collection efficiency of the substrate. Here, as you can see, we can get a semicircle indicating that we have adsorbed species at the interface. As you can see, this time constant is about 1 Hertz, and we cannot obtain it directly from the impedance measurement here. If we have a look on the capacitance plot, we have the relaxation time constant, and we can evaluate here 3 millifarad per square centimeter with a low frequency limit, and the integration of this low frequency limit allows to evaluate the charge stored at the interface, and we obtain the usual value of about 210 microcoulomb per square centimeter. So here we can obtain all what happened at the interface for the relaxation of the intermediates, and we can also get the relaxation frequency of the intermediates. But we can also try to, I'm sorry for the arrow, it's very awful. We can also try to simulate these results. So if we assume that it's a Tafel mechanism, we can fit the CV curve, and we can fit perfectly the capacitance results, here, the red curve, and the kinetic constant obtained are in rather good agreement with data obtained from the literature. But if we assume that it's a Volmer-Revsky mechanism, the result, we can fit here the CV curve, but we cannot fit the capacitance of the electrode. And the charge obtained at the end is much more smaller than the one we get experimentally. So this is a way of investigating adsorption at the electrode interface, but we can also investigate dissolution process, for instance, in the case of pure iron in a sulfuric acid solution. So this is the CV curve of for the dissolution of iron without the correction of the ohmic drop and with the correction of the ohmic drop. And all the experiments are performed for low overpotential here, because if we are performing experiment here in this domain, the dissolution is too wide, and the distance between the probe and the substrate change with time, and we cannot have a constant distance during the recording of an impedance diagram. So if we investigate this domain, we obtain for the impedance diagram a capacitive loop and an inductive loop. The amplitude of the loop varies with the potential, or it diminishes with the increase of potential because we have a larger current each time. And here in the low frequency, we have an inductive loop which is ascribed to the adsorbed relaxation. So usually in the literature, we can find two different mechanisms for this kind of dissolution, the Bockris mechanism and the Oechsler mechanism. The Bockris mechanism assumes the formation of an adsorbed species here and then a second electron exchange, whereas the Oechsler mechanism assumes the formation of an adsorbed species, and this adsorbed species acts as a catalyst for the iron dissolution for the next step. If we write the mass balance, we have very similar equation. The same goes for charge balance and the flux of electroactive species. So if we want to simulate the impedance diagram, we can find something good for the Brock-Reese mechanism and for the Osler mechanism. So it's not so easy to discriminate which one is the good one, if the Brock-Reese mechanism is a good one or if the Osler mechanism is a good one. Because in both cases, if I increase the potential, I decrease the amplitude of the diagram, I have a small shift of the characteristic frequency. Each time I have a capacitive loop and an inductive loop. So from this diagram, it's not so easy. Now I calculate the kinetic emission efficiency and for 3 different potentials. And as you can see, I just see a small shift of the frequency here. And if I perform the simulation for the Brock-Reese mechanism, I have something very similar. But if I assume that it is the Osler mechanism, here I have a change in the high frequency limit, depending on the potential. So here we have to go to the Brock-Reese mechanism, as already stated in the literature. The last thing I want to show you is that we can also perform this kind of local measurement without using redox mediator, by using a local electrochemical impedance spectroscopy. So instead of using a single probe, we are using a B microelectrode, and this B microelectrode is used as a local probe to sense the local potential at 2 different locations in the close vicinity of the substrate. So in that case, we do not need any redox mediator, and this potential difference here is directly linked to the local current density close to the substrate. So this is also a way to investigate adsorbed species. So we did the same thing than before for the iron. So we investigate 2 different potentials. So at a small over potential, we have an inductive loop and a capacitive loop and an inductive loop. Whereas for larger over potential, we have an capacitive loop, and another small capacitive loop. Now the frequency on this plot refers to this dimensionless capacitance here, with the pulsation, the double layer capacitance, the electrode size, and the electrolyte conductivity. Now if I perform local impedance measurement at the electrode center or at the electrode edge, depending on the position of the probe at the electrode surface, I will change the size of the inductive loop for the potential 1, whereas for the potential 2, I also evidence a capacitive loop and an inductive loop. What is interesting in this technique is that we are measuring indeed the local impedance. We can also measure the local interfacial impedance, and we can calculate this impedance, the local ohmic impedance. And this is the relaxation of this local ohmic impedance that will allow us to discriminate between the 2 mechanisms. For instance, if I calculate the local ohmic impedance for the potential 1 at the electrode center and for the edge, so this is experimental results. So we have this one is for the edge, and this one is for the electrode center. If I perform the calculation with the finite element simulation, we get exactly the same thing. And this part here, this one, is the same than, I'm lost, I'm said bad thing. If I investigate this domain here, that is the enlargement here, we get exactly the same thing by calculation, 2 time constant. Whereas here, if I investigate what's happened in this domain, I obtain these 2 time constant. So for the potential 2, we have this kind of snail for local impedance, and the calculation gives exactly the same thing. So we can get only these results when I use the Brock-Reese mechanism for describing what occurs at the interface. If I use the Osler mechanism, I'm finished. If I use the Osler mechanism, it's not correct. So to conclude, I hope that I show you that the scanning electrochemical microscope using in transient mode, like impedance measurement, allows us to characterize adsorbed intermediates. We can also obtain information for the mechanisms of what occur at the interface. And the local electrochemical impedance spectroscopy is also an interesting approach to perform the same kind of analysis without redox mediator. And I would like to thank some of the co-workers in the LISE, so Michel Kedam, Daniel Rose, Bernard Tribolet, and Dao Trin. And some colleagues, Ramon Novoa in the University of Vigo and Marc Orazem in the University of Florida. And I thank you for your attention.
In your interrogation of hydrogen, you were basically using the hydrogen proton pair to study that process, right?
Yes.
And at what potentials were you typically measuring that? Because when you get the full monolayer, you should be close to 0 volts, right? Yep.
Yes.
Or well, that's versus.
Yes. Because I have to say that in this domain, I can use very large sine wave perturbation because I respect linearity. So that's why I can scan the substrate potential in this domain here in the hydrogen production, but also in this domain. And I bias my potential, my electrode potential at this between 0 and 0.1.
Sure. So the longer question is, so there is a lot of discussion about the role of over-potential deposited hydrogen in the hydrogen evolution reaction, not only for platinum, but also for platinum, palladium, and or the other alloys, and whether this is the active intermediate rather than under-potential deposited hydrogen. So the question is, can you, the comment is, can you comment on the ability of your technique to explore further negative, under conditions where you have production of hydrogen under.
The main problem won't be the mechanism, the main problem will be bubble in that case, because we have to avoid bubble formation. All experiments were always performed with small overpotential in order to avoid bubble, because we cannot calculate the amount of charge generated for bubble formation. And if I want to perform a quantitative analysis, I need to know this amount. So I cannot go to larger overpotential, just for these reasons.
Sure. Low concentrations of perchlorate might work, so that could, of perchloric acid. That could be.
Thank you. One question?
Thank you for a good talk. Could you please comment on the complex collection efficiency as a function of the distance between two electrodes? In particular, if there is some goal, let's say, optimal distance where the first term in your equation would be neglectable.
So no, you have to remain in the diffusion layer of your substrate. You have to bring your tip in the diffusion layer of your substrate in order to detect something. But you can perform experiment from a few micrometers to up to 50 or 100 micrometers. You just have to calibrate your experiment at the same distance for diffusion than for your experiment you are interested in.
Thank you.
What is the locality of your measurement? You say it's a localized impedance measurement. What is the local resolution? Or do you have any
For which technique? Because easy for us, for the scanning electrochemical microscope, I can use a nanoelectrode. So this can be done on very small area.
But that doesn't mean that your resolution in the image is also that small like the probe, because you have a broadening of the diffusion fields and also the electric field distribution is broadening.
Yes, but when
so that's my question, in fact.
When you are performing this kind of measurement, when you are using a small probe, you have to bring your probe closer and closer to the interface. So if you are using a very small probe, I think that the resolution for the scanning electrochemical microscope for this kind of setup is about the size of the probe. For the local impedance technique, it's not exactly the same problem. Here it will depend on the distance between these two probes because we sense the potential difference in solution. And this is indeed the main problem. So here we cannot go at a value smaller than 1 micrometer for the spatial resolution.